Well, good day. My name is Berkenda. I'm the Director of Operations and Strategic Projects here at Omniair Consortium. Before we get started, I have just one housekeeping reminder, and that is questions are definitely encouraged. We will have time for Q&A near the end of the presentation. However, you may submit questions in the Q&A box as they come to mind. You don't have to wait until the end. I do see quite a few familiar names on the attendee screen. Hello, everybody. But for those who we have not met, Omniair is the leading industry association promoting interoperability and certification for connected vehicles, ITS, intelligent transportation systems, and road tolling technology device manufacturers, ITS deployers, testing laboratories, and other stakeholders, all promoting the proliferation of certified interoperable devices. For nearly a decade, we have provided the opportunity for members to work collaboratively to develop and determine the requirements for a national certification program. Our nearly 100 members have the opportunity to shape the future of ITS and IoT technologies and to work with industry leaders and transportation professionals to accelerate their interoperability. Today, we are so pleased to have a leading expert on post-quantum cryptography and also one of our member partners here with us. Márton, if you could please join me on the screen, that would be great.
Hi, hello everyone, thank you.
Hello, okay, so it is my pleasure to welcome Márton Isho. Thank you so much for making time for us today. Now, before I turn it over to you, I did tell you I was going to do this. I do want to share a little bit about who you are. So Márton Isho is currently employed at Microsec as a developer and expert in V2X and PKI post-quantum cryptography. He participates actively in the development of the CCMS and SCMS PKI. Excuse me. His journey with post-quantum signature algorithms began during his time at university, followed by engagement in several small projects with Microsec. These projects were associated with the NISD competition qualified algorithms. Since then, he has maintained an active presence in the field, diligently tracking its advancements and participating in various working groups dedicated to post-quantum cryptography, including the ETSI post-quantum sub-working group. And with that, thank you so much for joining us again. I'm going to go ahead and turn this over to you, so I know you're going to go ahead and show your slides.
Okay, thank you for your introduction. And I'm share my screen, and hopefully you can see my slides.
Okay.
And thank you. And yeah, I'm Márton Isho, and just a few words about Microsec. After my introduction. So Microsec is working in the security field for so many years, and we are dealing with digital signature certificates and so on. We started dealing with V2X for 6 years now. Since then, we developed and or also maintaining this, the European and the American standard regarding the V2X PKI. So in short, this is my company, and now let's move on to our presentation today. For my presentation, I would like to cover 3 main points. These key points are very important to show together how can we work with the post-quantum algorithms within the V2X environment. First of all, I will give you a quick overview on quantum computers. Where are we now? What can they do now? What the capabilities they have right now? After that, we will go a little bit into the details regarding what are the differences between a classical and a quantum computer. But don't worry, I would like to keep it on a high level overview. I don't want anyone to fall asleep just in the first 5 minutes of the presentation. So this will be just a highlight of the background of those computers. The second main point is the NISD competition. I will talk about what they did in the past, what are they doing now, and what they will do in the future regarding the post-quantum algorithms. And I brought you some comparison between those algorithms that they were chosen from this NISD competition. And our last point is the post-quantum algorithms in V2X PKI. And I brought a very interesting case study regarding this, regarding how can we include those algorithms into the V2X messages, and how can we communicate in a V2X environment with post-quantum algorithms, or with using post-quantum algorithms. So that's are the main points. And now let's move on to our first point, which is a general overview on the quantum computers. I am pretty sure that everybody knows at least something or just one thing about quantum computers. So I don't want to speak a little bit too much about these computers. And we all know that those computers slowly but steadily improving. In capacity, in speed, and in efficiency also. We're hearing news regarding these quantum computers time to time. Regularly, we are hearing some updates on those computers. For example, they found another solution how they can measure those qubits, or they reached a much bigger qubits in one quantum processor. So regularly we keep hearing news regarding these computers. They are there, they are slowly improving, but they are steadily improving in time. But which are the most recent machines out there? There are a lot of quantum machines that we know. First of all, I would like to mention the IBM one. It is interesting because IBM was the one who announced just last year, end of last year, that they have such a quantum processor which can hold up to 433 qubits in their system, and nowadays this is the biggest qubits in a quantum processor that we know. And the more interesting part is that they announced that they will have or they are planning to create 1,000 qubits processor by end of this year. I don't have any news regarding this, but they have they have still some months until the end of this year. So we hopefully will see a new update on this part. But beside IBM, there are a lot of other machines. There are Google and Intel quantum computers, but I put here some others which might not really not really known, like Riken. It is from Japan. It is a Japanese quantum computer. And there is another interesting one, is this IonQ, because it is as far as I know, it is the first commercial use quantum computer. So we can say that there are many of them out there, and a lot of people working on quantum computers. But where are they originated? The first quantum computer was built in 1998 with only 2 qubits, and I put this sentence here just because if we take a look at the classical computers, they are originated in the 1940s. And if we take a look at how far they got from almost under almost 100 years, then we can think about what we can expect from 100 years of evolving or improving of the quantum computers. So this is the situation now regarding the quantum computers. And now let's see what are the main differences between a classical and a quantum machine. The main and the biggest difference between those machines is the basic unit what they are used. As you might know, in a classical machine, we're using bits as a basic unit, and we can measure this by measuring the electricity in the circuit. So there is a 0 or a 1, there is on or off. So we can easily measure whether is there electricity or not, and we can decide whether it is a 0 or a 1 bit. But what is the situation regarding the quantum computer? In a quantum computer, we are using the same wordings. So we also call it bits, but we call them as a qubit, like a quantum bit. And these quantum bits are a little bit different than the classical bits, because one quantum bit can be placed in a superposition, which means if I have a 0, for example, on the input side, then this 0 on the output side can be 0 and 1 at the same time. So because of this, we can say that qubits can hold twice more information as bits. And to give another example, if we look at the classical bits, we can represent 4 different ways with the bits, 4 different basic way. For example, 0, 0, 0, 1, 1, 0, or 1, 1. And we can represent these 4 versions just with only 2 qubits at the same time on a quantum computer. So we need 4 different versions in a classic bit using classical bits or classical machines. But we need to. But regarding the quantum computers, we only need to use just 2 qubits to represent all the 4 versions. So this will lead us to our next point, which is the classical machines working as a deterministic machine, and on the other hand, the quantum computers working as a non-deterministic machines. Those definitions are, these are defines how a machine works. The deterministic machine, in case of a deterministic machine, we always know which state we are at a time. For example, if we get something on the input side, we will exactly know which state we will be on the output side, and so on. But in case of the quantum computers, which works as a non-deterministic machine, we are speaking about quantum states in this case. And if we got something, if we get something on the input side, then on the output side, it could be 1 or more different states at the same time. So it works as a non-deterministic machine. And this property gives the biggest advantage of this quantum computer, which is the problem-solving speed. So a quantum computer can work parallel and solve the problems parallel So it very it very gives a boost towards solving some different problems, but it should be stated that it won't apply to all problems in our world. So there would be never there would never be a state when only just quantum computers exist. There will be always classical computers beside them, but we can take advantage on this property on a quantum computer, and we can use, for example, during machine learning, optimization, simulation, quantum computers to speed up this problem solving speed. To talk about some drawbacks regarding the quantum computers, I would like to take it as a short overview, because this is not the main topic to our presentation. So, but we also need to speak about some drawbacks, some disadvantages regarding the quantum computers. First of all, it's based on another theory than the classical machines. So it is based on quantum physics, which is far from trivial, and very few people who understand this field in the world, and this makes it very costly to build such a computer. And the other main drawback is how can we measure those qubits? Because if we would like to operate those quantum computers and we would like to solve a problem, run a code on that computers, we need to measure those qubits, and the threshold, the window where we can measure those qubits are very short, is very short, because they need to be a so-called coherence state to be measured, and this time is very short during the operation of a quantum computer. It is about millisecondum, so like a 50 or 100 millisecondum coherence time. So it is a very short time where we can measure those qubits and calculate with those qubits. So the main focus and main goal during the development of a quantum computer is to produce less errors and handle those decoherence, because after the coherent state they will enter the decoherent state where they are not so stable and they cannot be measured so precise so well. So we need to handle this decoherent state, and we do it so by extending the coherence time. There are many techniques for doing so, like using ion traps, magnetic fields, putting down the temperature pretty low, or there are a lot of versions, but this also a main problem regarding the quantum computers. But the reason why are we here now are the threats that a quantum computer can hold. Now I will focus just on the technical threats and more precisely on the cryptography part of these threats. So what can we say now? We are using today two types of cryptography. The first one is the asymmetric cryptography and symmetric cryptography. And I think I'm pretty sure that you already heard some news regarding this, that symmetric key cryptography cannot be broken by a quantum computer. They can stand against those computers, and they will be fine in a post-quantum world. But are they really stand against a quantum computer? I think the answer is it depends. If we take a look at the mechanism behind symmetric key cryptography, we will see that we are making we have inputs, and we put this input into blocks, and we do some transformation on those blocks, and at the end we will have the ciphertext, the encrypted message, and the key is the same on the sender and on the receiver side also. So we are doing the encryption and the decryption with the same key, and usually we are not transferring this key on the internet, because it's not too safe to send a symmetric key just plainly or via the internet. So we are using some offline methods to bring this key to the other part, to the other party, and from this point of view, we can say, okay, you cannot eavesdrop the network, and you cannot catch the symmetry key because we transfer it offline. Yeah, that's fine. Yeah, that's true. But there is a attacking model where we are using a so-called exhaustive search, or with other words, a brute force attack. When we are try all the possibilities of the keys, and if it works, then we found the key. With classical computers, the symmetric key cryptography is safe against this type of attack. But as we saw earlier, a quantum computer can do it parallel, and they can solve a problem, and so they can do an exhaustive search parallel. So they can speed up this search, and yes, they can find the key. Not in a 1,000 year or so, as in case of a classical computer, but in just a few hours or few days. But what we can do regarding the symmetric key cryptography, we can increase the bit size of those keys, and we can increase it so that it would cost much more to make an exhaustive search on a quantum computer, and it won't benefit to run such an algorithm on a quantum computer. So we can say that we can parry this type of attack and this type of threat regarding the symmetric key with increasing the bit size of those keys. But what about the asymmetric key cryptography? Why are the asymmetric keys are more in danger? Because they are based on mathematical problems, not just block ciphers. There are some mathematical theories behind those algorithms. For example, behind the RSA, that is the so-called factorization problem. We have a big number, and we try to find factors that are primes. So and it is hard to find such a factors of a big number. Or for example, in case of the ECC, the mathematical problem is we have a curve, and we choose a random number, and pick a base point on a curve, and we multiply with this base point with the random number, and the result is a key. Result is a point also on the curve, and that will be the public key. But if you just know the public key, it is not easy to find out what was the secret key, which was that random number. So these are the theories behind the recently used algorithms today, and those kind of problems can be solved by quantum computers easily, and that's why are they in danger, because in case of a classical computer, it would take a lot of years to probe those, but in case of a quantum computers, it would take only just a few days or maybe a few hours to solve those problems and give the result of those problems. But what can we do if we as we saw the threats what a quantum computer can hold? What can we do against these threats? So yeah, first idea, let's find an algorithm that is cannot be broken by a quantum computer. So find another mathematical problem. There are a lot of mathematical problems in the world. So we just need to find one which cannot be broken by a quantum computer. So we need to find such hard mathematical problem and we need to use that mathematical problem, with this we at least we can say that this problem cannot be broken by a quantum computer, but we will see it's not so easy to find those algorithms. And as you might remember, on the previous slide, I told you there were classical computers beside quantum computers also. So we need to find an algorithm that can also work on classical computers. We should be able to generate keys, generate signatures, verify signatures on classical computers. So there is another restriction regarding finding an algorithm that we need to use it on classical computers also. It is not an easy task, and it is also not trivial to find such an algorithm, because most of the time they are much harder to implement. They are much harder to implement. The theory behind them sometimes is too new, and we don't understand each part of the problem. So sometimes it happens that someone finds a shortcut in the algorithm or in the theory, and break the algorithm. So it is never trivial to find an algorithm which can stand against a quantum computer. And this slide leads us to our second point, which is the NISD competition. Because the NISD just did the same thing as we talked about on the previous slide. So they started a competition regarding post-quantum algorithms in 2016, and their goal was to find both encryption and signature schemes that are good for different parts of our digital environment, and that are based on different mathematical problems. And there were a lot of options. There were a lot of algorithms that they get into the first round, and this competition lasted for 4 rounds. And I think, if I'm not wrong, it ended last year. The last post-quantum conference was at the end of last year. So they finished this competition, and they have chosen 4 different algorithms. The first one is the CAM, is a CAM algorithm. It is for encryption. It is an encryption scheme. And in short, the CAM stands for key encapsulation mechanism, which means during the encryption process, we are using symmetric and asymmetric keys. We are generating a symmetric key and encapsulate it with a post-quantum public key, so we are encapsulate this symmetric key with the post-quantum algorithm. This is the only one from the encryption section, and there are three signature schemes that were chosen for standardization. And for the next slides, I will talk about a little bit about these signatures, and we will take a little deeper look at those algorithms. First of all, I have to say that all post-quantum algorithms have bigger sizes regarding the keys and signatures. Maybe if you take a quick look at this at the last column, then the Sphinx Plus, maybe it's a little bit smaller compared to RSA, for example, but in general they are much bigger in keys and in terms of sizes regarding keys and signatures, and they are based on different mathematical algorithms. For example, the Kyber, dilithium, and Falcon, based on the so-called lattice-based problem, which is in short, we try to find the shortest vector in a given lattice. In basics, this is the main idea behind those algorithms, and the short vector is the private key, and we will give another vector as a public key, and it is hard to find that shortest one. Just in short, this is the main idea behind the lattice-based algorithms. And the last one, the Sphinx Plus algorithm, takes advantage of the hash algorithms. They are using it is using hash algorithms as keys, and they are building trees where the leaves are the private keys, and each parent node is a public key, and in this version, in this type of algorithms, we can only use one private key just for one signature, and we need to drop that private key. So they are so-called one-time private keys, one-time signatures. We cannot use another for another signature the same private key. This is the main idea behind those algorithms. And now, if we take a short look at the table, I'm sorry. The first, I need to tell you something first, because you can see ranges within the columns, and or within the cells, and that the reason behind that the NISD gave 5 different levels where the algorithms should be. The first one is the weakest security level. The fifth one is the strongest security level. That's why you can see those ranges within those cells. Sometimes, in case of some algorithm, there is no solution for every security level, but all of them made at least for two security level a possible solution. So if we take a look and take a look at this table now, we can say, yeah, I would like to highlight, for example, the last column for the Sphinx Plus, where if you check the signature size, it is not a typo. That is the exact number. So in case of a Sphinx, on the highest security level, we will produce almost 30 kilobytes of signature. So it is very huge, and the reason behind I would have liked to highlight this, that we will talk about the V2X part later, and we can clearly see it just right now that it is far from from those sizes that we can allow within the V2X messages. But regarding the others, we will see how they can they fit within the V2X system, but at least they are a little much more bigger than the now they used RSA or ECC, or now they used ECC within the V2X system. Regarding the speed, it is pretty hard to compare those algorithms, because they were benchmarked on different machines, different processors, different chipsets, and it is a little bit hard to compare how can they perform regarding the ECDSA or RSA, for example. They already have many different acceleration methods. They are using different chipsets, and for example, for Intel AVX2 chipset, and so on. So there are many other factors that can result differences between these measurements. So for now, I brought you actually I brought these values from my thesis from the university, because my task was to compare those algorithms. Those algorithms are the second round implementation, and it is necessary to state this because they improved since then, and the values might change regarding the speed. So if we take a look at this table, then we can see that regarding the performance, they are performed very well compared to the ECDSA, for example, because we are using this one in the V2X messages. So they are they are much less in speed regarding the ECDSA in some cases, but not every cases. And as I see, I'm just a little bit running out of time, so I'm sorry, but I will speed up a little bit. I talk too much, so let's move on. What NISD doing now? They started the standardization process. They made 3 drafts that are already available, and they are already made a new call regarding those post-quantum algorithms. They are focusing now on the signatures only. They would like to see other signatures, not just lattice-based signatures, and they would like to see better performance. They would like to see algorithms that have better performances and have smaller keys and signatures. I think these slides will be available for you, so you can click on the link and jump just right to the page where it is stated, so you can take a look at there. after. I brought you some interesting, three interesting problem. Just in short, I will go through it quickly. The first one is the isogeny-based problem, which is exactly, we can say it is an upgraded elliptic curve cryptography, because we are using elliptic curves, but we're doing some transition on them, and the result also on elliptic curves, which holds the same property as the first one. It is very interesting, I think. The second one is MPC in the head, the multi-party computation in the head, which based on the zero knowledge proof. It is a pretty new field, and I think it's very interesting how they can work in a post-quantum world. In short, it is each party have some little part of the secret. They are running on a function, and they will find out the result without giving out their secret. So I think it's also an interesting one. And the last one is the symmetric based, where the private key is a symmetric key, and the public key is a plain text ciphertext pair, which is generated by that symmetric key by encrypting a random message. I think it's very interesting, and it is a very new idea. And below here you can see the sizes regarding those algorithms. There are different approaches regarding using the post-quantum algorithms. In the EU, they are thinking about a hybrid version. They would like to use classical keys and post-quantum keys together. And as far as I know, in the US, they are thinking about a non-hybrid version, but maybe the audience know it better. I just heard this information that they are thinking on just using only post-quantum algorithms. But what we know is that in the EU they are giving out regularly algo papers, which contains all the supported algorithms. And for example, in the last algo paper, they extended the supporting of the RSA, and they did not mark any end date for the ECC regarding the support. On the US side, there is an NSA roadmap. They already announced a roadmap regarding this commercial national security algorithm suite, and they made a timeline with this transitioning, and they only suggest the dilithium algorithm as a default post-quantum algorithm. I think it's also a little bit interesting how these regions think about these ideas. What else we should know regarding the post-quantum algorithms? There is no unbreakable algorithm, only one that has not broken yet. So we could never be 100% sure about the secureness of an algorithm. For example, there is a psych which was in the competition, and before the fourth round, maybe. The implementer said there is a shortcut during the algorithm, so that with 100% of possibility they would be able to reproduce the private key. So that's why they sorted out from the competition. So we cannot be sure about the secureness, 100% sure about the secureness of an algorithm. But what we can do instead, we can do it just what the NISD does, which is make it widely available, give to everyone to research on it, try it, benchmark it, and so on, to find out where it should be improved, or is it can it be broken or not. And we can also think about that if it is hard or unclear, why even talking about it? It's just because the quantum computers are improving, are developing, evolving, and they are already there. And there is another reason which is there is already a potential attacking model, which is when an attacker saves the keys and the ciphertext for later, and after he gets a capable quantum computer, then he will be able to break those keys and the ciphertext. So we need to keep our eye on those news. And what about the V2X PKI and the post-quantum algorithms? This is our last topic. And in general, the V2X, we can say it is a little bit special field from this point of view, because we are using devices, we are using CAs, but right now I would like to focus on devices because they have smaller resources. And the devices changing messages very quickly. They would like to send, create, encrypt, or sign messages very quickly, and also verify the received messages. And they need to do it so that the size of the messages is fixed. So the post-quantum algorithms need to be fit in those messages, and let's see how can they perform regarding this this point of view. Here is the study about using post-quantum algorithms within the BSMs. It is from the University of Waterloo. They had this presentation on the third post-quantum standardization conference, and they made a little environment where they used the ECDSA algorithm, which is according to the standard, and they tried the dilithium and Falcon and Rainbow. Rainbow is a little bit, it is another type of algorithm which was not selected. I won't talk too much about this algorithm. I would like to focus on dilithium and Falcon. And from this first table, you can easily see that the dilithium is already out just at the first step because of its size of the signature. Dilithium, the second level of dilithium, has such a big signature that is already just only the signature itself exceeds the size of a BSM, so it is already out. And but in case of a Falcon, we can see that it just fit in the BSMs if we are using explicit search within the messages. But I have to state that this Falcon 512 is the first level of security. If we would like to use the highest level of security from Falcon, I think it would also exceed the packet size if we are using the explicit search within the BSM messages. So on the first round, dilithium is already out, but let's see how they perform regarding the speed. They made a measurement, and according to the measurement of the University of Waterloo, the maximum number of ECDSA verifications is 2,500 BSM per sec. And in a high density area, they measured 3,600 BSM per sec. And even the ECDSI cannot reach that number of BSMs. So such a high density area, we would not be able to use efficiently the ECDSA even. But regarding the dilithium and Falcon, they perform very well regarding verifying those number of BSMs. So we can say after this case study that if we are using the first level of Falcon, then it would fit into the V2X PKI. What about the new algorithms? Regarding the new ones, we can say we are almost on the same side. We are almost have the same situation. We almost have the same situation because the size of the signatures are way too big for V2X messages. Only that isogeny-based algorithm seems to be potential as an alternative. It should be good, and it is worth it to follow the news regarding this SQI sign algorithm, because it's based on the ECC. We're already using V2X within V2X ECC, ECDSA. So we expect a similar performance to that algorithm. Of course, it will be a little bit bigger in sizes, maybe a little bit slower, but we will see how it will come out. And until then, what we can do, because there is no capable quantum computer yet. There is no region-wide or worldwide V2X deployments. And so I think we have time to think about what we should do when a post-quantum world comes. And from now, I would like to pop up some thought-provoking ideas and questions regarding this V2X PKI and what can we do with our messages. So firstly, let's take a look, where are we using keys and signatures within V2X PKI? We are using those keys and signatures in CA certificates, different long-term and short-term certificates, pseudonym or individual certificates, in trust lists, as we are including certificates into the trust list and sign those trust lists. And in communication, under communication, I mean the V2V communication, from OBU to OBU or OBU to RSU and so on. So the device communications. And where is it necessary to focus on the performance? If you take a look at this list, the only reason where we need to focus on the performance is the communication, where we exchange messages very quickly. We would like to generate, sign, and verify those messages very quickly. And here comes the idea. What if we do not use post-quantum algorithm in every part of V2X, where we can use post-quantum? We can use those algorithms within long-term certificates, because in a CA certificates, we don't change those certificates too much or too quickly. For example, in case of an enrollment certificates, we also do not change those certificates quickly. And where is it questionable? For example, in case of the short-term certificates, so authorizations, authorization certificates. And the idea is, what about a hybrid solution, where we can use the classical keys? If you just using those classical keys just within the authorization certificates, we would be able to use such a hybrid model where the requests, where the long-term certificates consist only post-quantum keys, post-quantum algorithms, and signatures, but within an authorization ticket, within an authorization certificate, for example, we can use the regular ECC keys. Because if we take a look at the request, I'm not sure how familiar with this one, but if we are doing a request to a CA, for example, to the SCMS RA, then we will put some part of a key in case of the butterfly key expansion. But if we don't use that mechanism, we will put the public key into the inner request, and we will wrap it into other structure, and we will encrypt that request to that CA. So with this case, we would be able to use a hybrid model regarding the authorization certificates. And this was that was all my presentation. And as a conclusion, I would like to give you some takeaways, three main takeaways from this presentation. First of all, quantum computers are not there yet, but we also need to keep our eye on them. We need to be prepared because they are slowly but steadily improving. The second one is the NISD is already actively searching. So what we should do is just following the news, what NISD does, and believe that NISD will choose wisely, because they are already focusing finding such an algorithm that not just one algorithm at all, but find algorithms that can be used many different parts of our digital environment. And the last one, that our field, the V2X field, is a little bit special. We need performance in some parts, but not every part. So we might think about how can we change our system. Of course, it needs to it will lead to a modification to the standards anyway, whether we're using a hybrid solution or not. And it will have a lot of consequences, because there are already devices, there are already HSMs, there are already CAs, there are already some implementations, and we need to change those. And just one quick idea, that for example, if we are not using a hybrid model and we are just thinking about using just only post-quantum algorithms, then what can we do, for example, with the butterfly key expansion mechanism, which is massively based on elliptic curves. So these are the main parts that I would like you to take with yourself to home. And thank you for your attention. I hope it was clear and it was understandable for you. And if you have any other questions, please feel free to ask, and I try to answer them. Thank you.
Márton, thank you so much. Oh my gosh, that was a lot of information. I actually have a couple questions here on the screen. Let me go ahead and pop those over where I can see them. 1 second. So it looks like we have a question from Ken Moshi. Ken asks, how much of the quantum threat to crypto is real? For example, exists today versus in theory?
Thank you for your question. How much quantum threat to crypto is real? It is real, because there are already quantum algorithms that can break those algorithms. Yeah, it is a hard question a little bit, because yeah, the algorithms already exist, but the quantum computer that can do such a thing or is not exist right now. So in theory, they can break those because we have evidences, algorithms uh, that would be able to break those algorithms. But right now, um, there is no such a machine that can run such an algorithm.
Looks like there's a second question from Ken. It says, are we going to have an issue where quantum resistant crypto will be too complex for current hardware, including ECUs and vehicles, to decrypt either at all or in a timely manner?
Yeah, it is also a good question. I think they are a little bit, they are more complex than the RSA or ECC, but the NISD will make the steps clear. How can we implement those algorithms? And I think we don't need to care about this part, because these drafts already consists those steps. How can we implement such an algorithm? And about the timing, as we saw on the slides, they perform pretty well. So they are. I think the time would not be an issue regarding the quantum algorithms. Yeah.
So I got a couple more questions. As I'm asking these last couple of questions, I'm going to launch a quick poll just to see what everyone's familiarity is. So go ahead, if you can, just answer that poll. You should have just popped up. I see that it's on the screen. So question is, this is from Jason Conley. Thank you, Jason. Jason is our executive director, as I'm sure all of you know. And as you can see, Márton, he says this is a very fascinating presentation. What lessons can be connected? What lessons can the connected vehicle community learn from other industries, for example, banking, and preparing for a post-quantum world?
Oh, yeah, it is also a great question. Thank you. What can we learn? I would say this preparing. I think we should learn how they started the prepare, how they started preparing for this post quantum world, and I think we need to think much further in the future, and do not wait for a quantum computer. So. We need to think about how can we put our not our, but put post-quantum algorithms into our system, into our standard, and at least make the room, make the space for such a modification to those standards.
Okay, that makes sense. Thank you so much. One last question here before we go into just a couple quick announcements. Jason also says, as a practical matter, how far away are we from Q-Day, the point at which quantum computers are capable of breaking cryptographic algorithms, especially those used for V2X, 1 year, 5 years, 10 years?
Mm-hmm. Yeah, it is it's a hard question to answer, because yeah, we never know. Yeah, at least I think we can we can say that they are a little bit far away from now. So I wouldn't say that someone will come up with a big and very capable quantum computer just in a year or so. So I think we can wait yeah, we should wait for such a quantum computer for many years, like 10 years, but I cannot say an exact number regarding this.
Okay, thank you. So I'm just looking, I just closed our poll and it looks like, so the question that was asked is, what is your level of familiarity with the post-quantum algorithms topic? It looks like many of our participants today are really in the beginning stages. Sorry, most of them are in the beginning stages. So again, thank you so much for kind of bringing this to the table, bringing this to our members in the community. We really appreciate it. Before I let everybody go, I do want to do some quick announcements. If you'll bear with me for 1 second, I'm going to pop up my screen. See if I can still present that. Okay, so we've got that presented here. 1 second. Okay, so what do we have here? So we've got some upcoming events. We have a lot of things going on. I feel like the fall is jam-packed. I feel like almost the time after the holiday that's coming up this week is almost like the new year with so many things happening. So next week on September 7th, we have our Aftermarket Security Devices Working Group. That's their inaugural session. Anyone can join that session. So if you'd like to join the session, you can email me. We also have a working group form. This group is on there. So you can go ahead and complete the form. We'll get you added to that inaugural meeting at least. September 18th or 22nd, we have our virtual testing event. We haven't done one in a while, I think since a couple of years ago. So we're excited to have this. We're going to host a testing event focused on implementing 1609.2.1, as you guys can read here. Tying in with that directly, we have September 18th. Looking forward to some great speakers. We have the 1609.2.1 testing for V2X security presented by Justin Anderson from the U.S. Department of Transportation, Brian Romansky from Integrity Security Services, and I believe it's also going to be Miranda Kumar. I believe if I'm saying that correctly, from Qualcomm and not William White, but Qualcomm will be participating as well. So please join us for that. That registration is now open. November 6th through 10th, we have PlugFest. It's really not too late if you'd like to go. We would love to have you speak. That call for speakers is now open. So go ahead and submit that. I will review those personally and get back to you. That QR code on the right, because there are too many links to post here, is a way for you to get onto our website and pop into each one of those. Also, directly following this presentation, I will send out these links for you guys to have it so you guys can go ahead and link on there yourselves. And with that, again, Márton, thank you so much for your time. I know it's evening your time, morning my time. I'm going to have breakfast. You're going to have dinner. Have a great night, everybody. And thank you so much for joining us. Okay, we'll see you next time.
Thank you. See you.